हेलो हेलो सर।
हाँ ये तो
ठीक है, स्टार्ट करते हैं। हम्म, Okay. Yesterday we have talked about first topic, dual nature of matter. Today we will discuss about second unit, that is structure of atom and nucleus. What is atom? Atom is smallest particle of an element which contains all properties of element. Okay. Then what is nuclear? Nuclear refers to a nucleus of an atom which consists having a given number of nucleons. Okay, so nuclear refers to a nucleus of an atom. Atom is the smallest particle of an element. Then, in the early days, different models regarding structure of atom and nuclear was proposed. So, first one, J.J. Thomson's plum pudding model. So, as per J.J. Thomson's model, atoms are just positively charged lumps of matter with electrons embedded in them, like resins in a fruitcake. Okay, but the outcomes are not that much fruitful. So, while studying the concept of emission of alpha particles by different radioactive elements, Rutherford have performed one of the experiment, that is scattering of alpha particles. Scattering of alpha particles by atoms for investigation of internal structure of atom. So as per the experiment Rutherford has performed, so he has proposed model that is known as Rutherford's model to know the structure of atom. Then, what are the outcomes of Rutherford's model? On the basis of his experiment, Rutherford concluded that at the center of atom there is nucleus of radius approximately 10 raised to minus 15 meter, in which entire positive charge and entire mass of an atom is to be concentrated. Okay, this is the first outcome. The second, electrons are distributed in a hollow sphere of radius nearly 10 raised to minus 10 meter. Means the concept of nucleus was put forward by Rutherford's atomic model. The total negative charge of electrons is equal to the positive charge of the nucleus. Then electrons do not reside stationary around the nucleus. Otherwise, the electrons, due to attractive force of positive charge of nucleus, will fall into the nucleus and atom will become unstable. Then after that, there are some discrepancies observed in Rutherford's atomic model. So Bohr's model was put forward. After Niels Bohr obtained his doctorate in 1911, he worked under Rutherford for a while. So in 1913, he presented a model of hydrogen atom. Okay, what are the outcomes of Bohr's atomic model for study of structure of the atom? He has put forward three postulates. The first postulate states that an electron in an atom could not revolve in certain stable orbits without the emission of radiant energy. Okay, so according to this postulate, each atom has certain definite stable states in which it can exist, and each possible state has definite total energy. These are called stationary states of the atom. Means what? As per Bohr's postulate, electrons are simply revolving in circular orbits around the nucleus, and the centripetal force necessary to perform uniform circular motion will be provided by the electrostatic force of attraction. That is the outcome of first postulate. Then the second postulate. Electrons are revolving in stationary orbits. Okay, so what is the condition? The condition to say that electrons are revolving in stationary orbits of which angular momentum is an integral multiple of h upon 2 pi. Angular momentum of the orbiting electron must be quantized. Angular momentum is equal to nh upon 2 pi. So electrons are revolving in stationary orbits of which the angular momentum is an integral multiple of h upon 2 pi. Okay, next one, Bohr's third postulate. As per the drawback of Rutherford's theory, Rutherford model can't explain the origin of spectral line. But as per the Bohr's third postulate, we can explain about the origin of spectral line. What it states that when the electrons from higher energy orbit are jumping into lower energy orbit, it emits the energy, it emits the radiations, okay, and that is causing to absorb the spectral lines. So as per Bohr's third postulate, when an electron jumps from higher energy orbit to lower energy orbit, it emits the energy in the form of radiations. And the frequency of emitted photon is given by h nu equals to E2 minus E1 or E of I minus E of F, where EI is the initial energy or the energy of initial state and final state, that is EF. EI must be greater than EF. Next, limitations of Bohr's model. Bohr's atomic structure, limitations. Then, so what is the Bohr's first postulate? Bohr's first postulate states that the electrons are revolving in circular orbits and the centripetal force necessary to perform the circular motion is balanced by the electrostatic force of attraction. That is first postulate. Then second postulate, electrons are revolving in stationary orbits in which the electron must possess the angular momentum equals to nh upon 2 pi. Then as per Bohr's third postulate, when an electron jumps from higher energy orbit to lower energy orbit, it emits the radiations. Next one. Then as per Bohr's first postulate, radius and velocity of electron in nth orbit. Let us consider an electron revolving around the nucleus in circular orbit. Then according to Bohr's second postulate, this is L angular momentum. Angular momentum is given by P into R. What is P? P is the linear momentum. Linear momentum is given by mv multiplied by radius of this particular circular orbit. So angular momentum is equal to nh upon 2 pi. Next, according to Newton's second law, this centripetal force must be balanced by electrostatic force of attraction. And this electrostatic force of attraction is given by E square upon 4 pi epsilon 0 into R square of n. This is the centripetal force necessary to have the uniform circular motion of the electron in stationary orbits. Then E square on 4 pi epsilon 0 R square of nth orbit this equation related with Bohr's first postulate. And if you're solving this equation, the first equation is mvr equals to nh upon 2 pi. So solving equation 1 and 2, we get r of nth orbit equals to epsilon 0 n square h square upon pi m e square. Similarly, by solving equation first and second, we can write nth orbit speed. This is speed of the electron which is orbiting in nth orbit equals to e square upon 2 epsilon 0 n into h. So all these equations you should remember while solving the MCQs asked for different MHT-CT question paper. Okay. Again, one more equation you should remember. Energy of electron in nth orbit. Energy of electron in nth orbit is given in terms of energy equals to m e raised to 4 upon 8 epsilon 0 square n square h square. So energy of electron revolving in nth stationary orbit is directly proportional to 1 upon n square. Okay. So if you're substituting the value of m as the constant, E charge epsilon 0 permittivity of free space, n that is the quantum number, is state, h that is Planck's constant. Then uh, energy of first energy state where the electrons are revolving, E1 equals to minus 13.6 electron volt. What is m? M is mass of an electron is given by 9.1 into 10 raised to minus 31 kg. E charge 1.6 into 10 raised to minus 19 Coulomb, epsilon 0, 8.85 into 10 raised to minus 12 Faraday per meter, H, Planck's constant, 6.625 into 10 raised to minus 34 Joule second. So by substituting all these values for an electron, you can obtain energy of an electron orbiting in first stationary orbit equals to minus 13.6 electron volt. Similarly, we can calculate energy of uh, the electrons which are revolving in different stationary orbits. Okay. Next definition for ionization energy. Ionization energy of the hydrogen atom is the energy required to remove the electron completely. Okay. In order to remove the electron, we should apply some energy, and that's called ionization energy. The energy required to take an atom from its lower state to higher state is known as excitation energy. And third one, the potential through which an electron should be accelerated to gain higher state is called excitation potential. Okay, all these points you should remember. Next, this is one of the major point in this structure of atom and nucleus. This is a hydrogen spectrum. So as per Bohr's third postulate, when an electron jumps from higher energy state to lower energy state, it emits the spectral lines. There are different series associated with this hydrogen spectrum. Here you can observe there are different energy states, n equals to 1, n equals to 2, n equals to 3, n equals to 4, okay, like that, n equals to infinity. So it goes up to n equals to infinity. So these are different series, Lyman series, Balmer series, Martian series, bracket series, and Fund series. When the transition of an electron is taking place from higher energy orbit onto the lower energy orbit having n1 equals to 1. Then it is associated with Lyman series. Okay, so Lyman series consists of different spectral lines. The first line will be observed by the transition of an electron from n equals to 2 to n equals to 1 state. Second spectral line among Lyman series is created by the transition of an electron from n equals to 3 to n equals to 1. Means Lyman series is providing a series of spectral lines where the transition of the electrons from higher energy states are taking place onto the lower energy state where n equals to 1. Similarly, when the transition is taken place on the second energy state, the transition is taken place on the second energy state, n equals to 2, it provides you Balmer series. And all these spectral lines are observed in visible light. Okay, so when the transition of an electron is taken place from n equals to 3 to n equals to 2, then we can obtain H alpha line. Similarly, when the transition of an electron is taken place from n equals to 4 to n equals to 2, it provides you H beta line. So all these are spectral lines among Balmer series, where the transition is taken place from higher energy orbit to the n equals to 2 state. Similarly, we have partial series, bracket series, and fund series. Means if the transition is taken place from higher energy state onto n equals to 3 state, it gives rise to partial series. Then bracket series. If the transitions of an electrons are taken place from higher energy orbit to n equals to 4 state, then it provides you the spectral lines which are associated with bracket series. Similarly, fund series. So this is the hydrogen spectrum. Here is one important formula you should remember. Lyman series. Wavelength of Lyman series can be expressed in terms of Rydberg's constant 1 upon lambda equals to R into 1 upon, because transition is taken place from higher energy orbit to lower energy orbit. That is n equals to 1. So 1 upon lambda equals to R into 1 upon 1 square minus 1 upon, means n1 square minus n2 square. Here for Lyman series n1 equals to 1 and n2 first line will be observed for n plus 1, that is 2 line, n equals to 2 line. Okay? So for Balmer series, this wavelength associated with the radiations emitted can be expressed in terms of Rydberg's constant into 1 upon 2 square minus 1 upon the n corresponding to the transition from which the electrons are jumping. Okay, the transitions from which the electrons are jumping into n equals to 2 state. So like that, we are able to calculate the wavelength of each spectral line among Balmer series. Next one, for partial series, we have seen that the transitions are taking place from higher energy orbit to n equals to 3 state. When the transition of an electron is taking place from higher energy orbit to lower energy orbit, it emits the radiations. And those radiations emitted are having the frequency in terms of the energy, that nu equals to difference in the two energies upon h. Okay, so like that we can calculate lambda associated with each spectral line observed in hydrogen spectrum. Okay, next. Next point, we'll discuss based on that you have to solve number of problems. We briefly comment on Bohr's second postulate. We have seen that lambda equals to h upon Lv. When an electron is performing its motion, then when the charged particle is in motion, the wavelength associated with the charged particle which is in motion can be expressed in terms of lambda equals to h upon m phi. Lambda equals to h upon p. But again, we know that in order to have the circular motion, it should cover complete circumference. So 2 pi r corresponds to lambda. In order to complete one oscillation, lambda equals to 2 pi r observed in nth orbit. So 2 pi r is equal to nh upon m into phi provides you the expression that n phi r is equal to nh upon 2 pi. N is the principal quantum number in which electrons are revolving. H is Planck's constant, m mass of the electron, v velocity, r radius of the stationary orbit in which electrons are revolving. Next, radioactivity. Becquerel discovered that heavy elements like radioactive substances having atomic number greater than 82. There also a spontaneous emission of radiations such as alpha particles, beta particles, and gamma rays. Okay, so from certain radioactive substances, radiations are emitted, and that phenomenon is called radioactivity. Then you have to solve radioactive decay law. According to this law, the number of nuclei undergoing decay per unit time. This is what disintegrations per seconds. Disintegration per second is directly proportional to number of nuclei present at any instant of time. Let us assume that NP, the number of nuclei present at any instant t, and Dn is the number of nuclei that disintegrated in short interval of time dt. Then there is a formula minus dn by dt is directly proportional to capital N. And this lambda is the proportionality constant which is called decay constant. Okay, so number of disintegrations per unit time taking place is directly proportional to number of nuclei present at any instant of t. Okay, so this equation can be expressed as dn by capital N equals to minus lambda into dt. And if you are integrating this over very small intervals of time, then integration from n0 to capital N equals to dn upon n equals to minus lambda, that is proportionality constant. We have to come outside integration from 0 to t dt. And if you are taking the integration, then we can obtain log of n upon n0 equals to minus lambda into t. Okay? That means we are having this expression n equals to n0 e raised to minus lambda t. And this function is plotted in this particular figure. Now, how to calculate the half-life time? What is half-life period? The time required for the number of parent nuclei to fall to 50%. म्हणजे एखादं एलिमेंट आहे त्याच्यामध्ये रेडिओएक्टिव्हिटी ऑब्झर्व होतीये, तर रेडिओएक्टिव्हिटीमध्ये अल्फा पार्टिकल्स, बीटा पार्टिकल्स आणि गॅमा रेजचं एमिशन होत आहे. सो ओरिजिनल न्यूक्लियापेक्षा हाफ ऑफ द पर्सेंटेज त्याचं डिक्रीज किती वेळात होतं त्याला म्हणायचं हाफ लाईफ. ओके, सो द टाइम रिक्वायर्ड for number of parent nuclei to fall to 50% is called half-life and may be related to lambda as 0.5 is 50% of original nuclei. 50% of original nuclei is equal to, here is the correction, 50% of original nuclei equal, that means it is capital N equals to N0 into e raised to minus lambda t upon 2. So, half-life period means what? ओरिजिनल सोर्स पासून जितके रेडिओएक्टिव्ह डिसइंटिग्रेशन्स मध्ये न्यूक्लिया एमिट होतात त्याचे हाफ होण्यासाठी लागलेला टाइम म्हणजे काय, हाफ लाईफ पिरियड. सो दॅट एक्सप्रेशन वी कॅन obtain is half life period t half equals to log of 2. This the equation in order to calculate t half, that is 0.693 upon lambda. And average or mean lifetime is the reciprocal of decay constant. So T average equals to 1 upon lambda. Lambda is what? It's a decay constant. So like this, we will be able to solve number of problems by having this particular background information. Now let us try to solve the examples. Okay. So we should remember few formulas. The first one, sir. Posle sir. Same color. Okay. So first formula, you should remember. First, MBR equals to NH upon 2 pi. Where R, that is radius of the nth orbit, where the electrons are revolving. Okay? And the second formula, MVR is simply angular momentum. Angular momentum is equal to NH upon 2 pi. That is as per Bohr's second postulate. Next formula, as per Bohr's first postulate, centripetal force necessary to perform uniform circular motion can be balanced by the electrostatic force of attraction and v square upon r. That is the centripetal force necessary to perform uniform circular motion by the electron. So it is balanced by Z into v square upon 4 pi epsilon 0 into r square of n. Okay? Then third formula, you should know, 1 upon lambda equals to r Rydberg's constant into 1 upon n1 square minus 1 upon n2 square. Hmm? And n1 and 2 values are different for different series that we have studied. So there are different series associated with the hydrogen spectra. So Lyman series, Balmer series. Hmm? For Lyman series, the first spectral line can be observed if you are substituting n1 equals to 1, n1 equals to 1 and n2 equals to 1 plus 1, that is 2. 1 plus 1, that is 2. If the transition is taken place from n2 equals to 2 on n1 equals to 1, then whatever the radiations are emitted, that particular lambda, we will be able to calculate. What is the value of R? R is simply Rydberg's constant, and that Rydberg's constant is calculated based on the formula that m e raised to 4 upon 8 epsilon 0 square, 8 epsilon 0 square h cube into c. Okay, so this is Rydberg's constant that is obtained simply by observing energy equation. That energy expression we have E equals to z square m e raised to 4 upon 8h square, 8h square epsilon 0 square into the transition is taken place from n1 square minus 1 upon n2 square. Obviously, n1 and n2 values are different for different series. As we know that E equals to h nu and nu equals to c upon lambda. Okay, so the same expression we can write in terms of c as uh, h nu that is sub, that is simply replaced by E equals to h into c upon lambda. E equals to h nu equals to c upon lambda equals to z square m e raised to 4 upon 8h square epsilon 0 square into 1 upon n1 square minus 1 upon n2 square. Okay? So if you are taking this hc to this side, then what we have obtained, that is simply z square m e raised to 4 upon 8 h cube into epsilon 0 square into c into bracket 1 upon n1 square minus 1 upon n2 square. And this constant is called as R. That is called Rydberg's constant, and the value of which is calculated by substituting m mass of electron, E charge on electron, epsilon 0 permittivity of free space, h is Planck's constant, and c is velocity of light. And that value coming as 1.097 into 10 raised to 7 per meter. Okay, this is the constant which is called Rydberg's constant. Fine. Okay, next. For Lyman series, n1 equals to 1, n2 equals to 2. And by having this particular substitution, we will be able to calculate the wavelength corresponding to first spectral line. If you're substituting n1 equals to 2 and n2 equals to 3, then we will be able to calculate lambda corresponds to second spectral line. Similarly, if n Similarly, if you are substituting n1 equals to 1 and 2 equals to 4, then we will be able to calculate the wavelength corresponds to third spectral line. Okay, this is about Lyman series. Similarly, we can calculate lambda 1, lambda 2, lambda 3 for Balmer series. Here, it is common that N1 should be substituted by 2 and N2 equals to either 3, 4, 5, and so on in order to observe first spectral line, second spectral line, third spectral line from Balmer series. Similarly, Lyman, Balmer, Paschen, Brackett, and Fund. These are different series. Lyman, Balmer, then Paschen. The spectral lines from Paschen series can be obtained by simply substituting N1 equals to 3 and N2 equals to 4, 5, 6, and so on. Then bracket series, fund series can be obtained simply substituting by N1 equals to 4, N2 equals to 5, 6, and so on. Then fund series can be calculated by just doing the calculation n1 equals to 5, n2 equals to 6, 7, and all that. Okay. So these are some formulas necessary to solve uh, different problems which were asked for different CT examination. Um, okay, just here. Let us read the first example. Using Bohr's quantization condition, what is rotational energy in the second orbit for a diatomic molecule? Okay. So they are asking to calculate the rotational energy. What is Bohr's quantization condition? That you first have to write. Bohr's quantization condition. It says that mvr equals to nh upon 2 pi. That means L equals to nh upon 2 pi. This is Bohr's quantization theory. But we know that angular momentum is expressed in terms of angular frequency as in terms of moment of inertia. L equals to I omega. That is first equation. Okay. And this is second equation. Both are the values corresponds to angular momentum. So we can equate. So I omega equals to nh upon 2 pi. nh upon 2 pi. Here, this is second orbit. Okay. So here n equals to 2. Here n equals to 2. Therefore, what we can write? I omega equals to 2h upon 2 pi. That means it's a h upon pi itself. I omega equals to L. L equals to I omega equals to h upon pi by using Bohr's quantization theory and the formula for angular momentum. Okay. Now, how to calculate rotational energy? Here, I is moment of inertia. Don't forget that. I is moment of inertia. Now, rotational energy can be calculated. Rotational energy equals to 1 half I omega square. 1 half I omega square. Okay. So that can be calculated by I square into omega square upon 2I. I square omega square upon 2I. But what is I omega? I omega is L. Therefore, we'll be able to calculate L square upon 2I. L square upon 2I. Okay. So we have MPR is equal to NH upon 2 pi. L equals to, as per Bohr's quantization condition, L equals to NH upon 2 pi. For the rotational motion, angular momentum can be expressed in terms of angular frequency and L equals to I omega. Therefore, I omega equals to NH upon 2 pi. Here, second orbit is given, N equals to 2. So, L equals to H upon pi. But we know that rotational energy equals to 1 half I omega square. Multiplying and dividing by I. So, we can write I square into omega square upon 2I equals to L square upon 2I. But they are asking to calculate L in terms of H and pi. So just substitute L equals to H upon pi. So rotational energy equals to L square is to be substituted by H upon pi bracket square L value into 1 upon 2I. Okay? So here is the answer h square upon 2I into pi square. So which option is correct? H square upon 2I into pi square. So this is the correct answer. H square upon 2I pi square. Okay? Understood? See the next example. So all these fundamentals you should know. Then only you will be able to calculate this. Next, the ratio of speed of an electron in ground state. The ratio of speed of an electron in the ground state in the Bohr's first orbit of hydrogen atom to velocity of light c. Okay. Uh, so again, we should take the help of the ratio of speed of an electron in the first orbit of hydrogen atom. Now again consider this formula. The centripetal force necessary to perform uniform circular motion by the electron in stationary orbit can be expressed in terms of mv square upon r, and that should be balanced by the electrostatic force of attraction. So it can be written as z into e square upon 4 pi epsilon 0, 4 pi epsilon 0 into r square of n. What is V? V is the speed or velocity of the electron, R radius of the orbit, E charge of the electron, epsilon 0 permittivity of free space. Okay. By knowing all these symbols, now you can express this as uh, again one more equation you should remember. MVR is equal to NH upon 2 pi. This is first equation. This one is second equation. We have to rearrange the terms to get the equation in this particular form. Okay? So now MVR equals to NH upon 2 pi. So mv square upon R. Mv square upon R into this R square of N, R square equals to Z into E square upon 4 pi epsilon 0 into, so this R square you have taken to another side. So 1 R will be getting cancelled. So what is left here? That is simply M V square R square m v square 1r will be getting cancelled. So m v square r equals to z e square upon 4 pi epsilon 0. Okay? What is mvr? Mvr is equal to nh upon 2 pi. So we can write that nh upon 2 pi into v. because we have to calculate the velocity. nh upon 2 pi into v equals to z e square upon 4 pi epsilon 0. Okay. For a hydrogen atom, Z equals to 1. For a hydrogen atom, Z equals to 1. And therefore, this formula for velocity of the electron in terms of V can be expressed as V equals to hmm, uh, this Z E square upon E square upon 4 pi epsilon 0 into 2 pi upon n into h. ठीक है? So 2 2s are 4. Pi will get cancelled. So what is left here? That is simply e square upon pi will get cancelled. 2 2s are 4. 2 epsilon 0 into n uh, into c into 2 epsilon 0 n into h. Okay. But they're asking the Bohr's first orbit of hydrogen atom to velocity of light. Here n equals to 1, first orbit, n equals to 1. Okay, so V upon C is equal to E square upon 2 epsilon 0 into H. V square upon 2 epsilon 0 into H into C, because here we have multiplied and divided by C. Multiplied and divided by C will provide you V upon C equals to E square in upon 2 epsilon 0 into H into C. So we will check here, the same is there. V upon C is E square upon 2 epsilon 0 H into C. So here is the correct answer. Okay, E square upon 2 epsilon 0 H into C. Okay, we will once again see the steps what we have done. In second, we have the equation centripetal force equals to means electrostatic force of attraction. We have the formula. Okay. Again, we have second equation, mvr equals to nh upon 2 pi. Okay. Rearranging the terms and substituting for a hydrogen atom z equals to 1, and for substituting n equals to 1, as they say is that it's a first orbit where the electron is revolving. Okay. So finally, we have obtained the equation V upon C equals to E square upon 2 epsilon 0 H into C. And that's the correct answer. Next one. Next. Okay. This very easy example. Just check it. Okay. The ratio of energies of photons produced due to transition of hydrogen atom from its second to first energy level. Okay, and second highest energy level to second level respectively. Then what is the ratio of energies? What we have the equation 1 upon lambda equals to 1 upon lambda equals to r into bracket 1 upon lambda. हे इक्वेशन लक्षात ठेवायला खूप सोपं आहे. 1 upon lambda equals to r into 1 upon n1 square minus 1 upon n2 square. Okay. Next, we want to calculate the ratio of energies. What we have E equals to h nu equals to h into c upon lambda. Okay. Therefore, this lambda can be expressed in terms of E as lambda equals to lambda equals to uh, HC upon E. HC upon E. Here we want 1 upon lambda, and therefore 1 upon lambda can be substituted by E upon HC. Okay. So what is the formula we have obtained? That is simply E upon HC equals to R into bracket 1 upon N1 square minus 1 upon N2 square. Okay. Now just check. Transition of electron of hydrogen atom from its second to first. That means second to first. That means N1 equals to 1. N2 equals to 2. Second to first. Okay. That that is first part. So we will write first equation. And second part, highest energy level. Hmm? Let us assume that for N1 equals to 1 and N2 equals to 2, we will be getting the equation E1. Similarly, highest energy level, that means N1 equals to 2, the transition is taken place from highest energy level to N1 equals to 2. So N2 equals to infinity. N2 equals to infinity provides you E2 energy level. Okay, just calculate that. So for calculation, you can write, okay, so what is the equation? Uh, by observing this as the fundamental, you can check E is to be replaced by E1. That HC we can take to another side. So R H C into bracket have the substitution N1 equals to 1, N2 equals to 2. So 1 upon N1 square minus 1 upon N2 square. Okay? This first equation. Then second equation, for letting E2 value, substitute N1 equals to 2, N2 equals to infinity. So by that, we will be getting E2 equals to R H C into bracket 1 upon uh, 2 square. Forget to substitute here. That I will substitute here. Okay, what should be here? It should be 1 square and this should be 2 square. 1 square because of this substitution. N1 equals to 1, N2 equals to 2, then only E is to be substituted by E1. Okay, that we will make here. Okay, 1 upon 1 square minus 1 upon 2 square because of given data. Now, to calculate E2, they are saying N1 equals to 2 and N2 equals to infinity. So, I have the substitution. So, 2 square minus 1 upon infinity square. So, we are getting second equation. Okay. Now, take the ratio of 1 and 2. So, if 1 upon E2 equals to R H C into bracket 2 square minus 1 square, 4 minus 1, that is 3 by 4 upon R H C 1 upon infinity 0, 1 upon 2 square, that is 1 upon 4. Okay. So RHC cancelled. So what is left here? That is 3 by 4 into 4 by 1. Okay. So what's the ratio you will be getting? That is simply 3 upon 1. आहे का बघा option आहे. So B, that is the right answer. B is to 1. E1 is to E2. E1 upon E2. E1 is to E2. will be in what proportion? 3 is to 1. E1 is to E2 is 3x to 1. So this is the correct answer. Okay? Understood? No next one. Next. Fourth one. Okay. The energy levels with transitions for the atoms are shown. The energy levels. A, the transition is taken from highest energy level. B, C, and D. So what they are asking from this diagram, the transmissions corresponding to emission of radiation of maximum and minimum wavelength are respectively. The transitions corresponding to emission of radiation of maximum and minimum wavelength. आता आपल्याला माहिती आहे की E equals to h nu equals to h into c upon lambda. Means E is directly proportional to 1 upon lambda. Means inversely proportional to lambda. Okay. Here, for a point, in order to get a spectral line, बघा इथे हा spectral line, a spectral line, where delta E is smaller. Delta E is smaller. Okay. And at point D, delta E is larger. Thus, at point D, that means for the spectral line corresponding to D, the difference in the energies is larger. Delta E is larger. ठीक आहे. म्हणजे इथे ट्रान्झिशन होत आहे हायर एनर्जी स्टेटवरून त्याच्यापेक्षा लोअर एनर्जी स्टेटमध्ये. आणि हा डिफरन्स इन एनर्जी जो आहे तो खूप कमी आहे ॲज कम्पेअर्ड टू हा एनर्जी डिफरन्स किंवा हा एनर्जी डिफरन्स किंवा हा एनर्जी डिफरन्स. ठीक आहे. द ट्रान्झिशन करस्पॉन्डिंग टू एमिशन ऑफ रेडिएशन ऑफ मॅक्सिमम अँड मिनिमम वेव्हलेंथ. मॅक्सिमम कुठे ऑब्झर्व होत आहे तर ॲट स्पेक्ट्रल लाईन ऑफ डी ह्या स्पेक्ट्रल लाईनचा हा डिफरन्स जो आहे तो एनर्जीच्या टर्म्समध्ये जास्त आहे. ठीक आहे. पण वेव्हलेंथच्या प्रपोर्शनेटमध्ये जर आपल्याला बघायचं असेल तर ॲट फॉर ए लाईन लॅम्बडा इज हायर. Lambda is higher. And here delta E is larger, but lambda is shorter. Lambda is shorter. Okay. So A corresponds to maximum wavelength. A corresponds to maximum wavelength. And D corresponds to, D is the spectral line which corresponds to minimum wavelength. Minimum wavelength. परत एकदा सांगतेय हा डिफरन्स जो आहे ह्या लोकेशनला म्हणजे जेव्हा इलेक्ट्रॉन या एनर्जी स्टेटवरून इथे ट्रान्सलेशन करणार आहे तेव्हा त्यातला डिफरन्स हा खूप कमी दिसतोय. ठीक आहे. म्हणजे ए इज द स्पेक्ट्रल लाईन which is observed due to delta E is smaller, whereas here D is the spectral line where you can observe the difference in the energies that are going to be emitted due to the transition of an electron from this energy state to this energy state. So there you observe delta E is larger, but E is directly proportional to 1 upon lambda. So we can say that A is the maximum wavelength and D is the minimum wavelength due to the transition of an electron as shown in figure. So let us take the transition corresponding to emission of radiation of maximum. Maximum ची spectral line A आहे. So this is right one. Maximum ची spectral line A आणि minimum ची spectral line B. So this is the correct option. Okay. Understood? Next, uh, okay. Using Bohr's model, the orbital period of electron in hydrogen atom in nth orbit. Okay, what they're asking to calculate, they're asking to calculate the orbital period of electron. Now let us check all the formulas. As we know that orbital period T is equal to circumference 2 pi r upon v, circumference of the circle upon velocity of the electron orbiting in particular orbit having radius r. And that's an orbital period आपल्याला काढायचे. T is equal to 2 pi r upon v. We have calculated the value of r by having the equation mvr mv square upon r is equal to e square upon 4 pi epsilon 0 e square upon 4 pi epsilon 0 into r square. Okay, that centripetal force equals to electrostatic force of attraction. By solving this particular condition, we obtain the value of r as r equals to epsilon 0 n square h square upon pi m e square. ओके, आता हे इक्वेशन आलं कसं, तर हे ऑलरेडी आपण बघितलंय, परत एकदा आपण रिवाइज करूया. Just here mv square upon r, but again we have the equation L equals to mvr equals to nh upon 2 pi. ठीक आहे, L equals to nh upon 2 pi equals to mvr. आता हे इक्वेशन आपण सॉल्व करूया. So what we can obtain, that is simply mv square upon r into r square equals to e square upon 4 pi 4 pi epsilon 0. ठीक है, mv square into r square. So mvr can be written in terms of L mvr into v square. ठीक है, into v mvr into v equals to e square upon 4 pi epsilon 0. Again, we have the equation in terms of v. What is v? V equals to e square upon 4 pi epsilon 0 into L, because mvr is equal to L. So this v, that is velocity, v equals to e square upon 4 pi epsilon 0. So v equals to e square upon 4 pi epsilon 0 into L. Therefore, the same can be written as v equals to e square upon 4 pi epsilon 0. L is to be replaced by nh upon 2 pi. So nh upon 2 pi, nh upon 2 pi. ठीक है. So what is the value of v we obtain? That is simply e square upon 2 epsilon 0 n into h. Similarly, We obtain by solving this, you will be able to calculate the value of r as epsilon 0 n square h square upon pi m e square. R is fundamental equation, radius of the orbit in which the electron is revolving. So R equals to epsilon 0 n square h square upon pi m e square. Similarly, we have obtained the equation V equals to E square upon 2 epsilon 0 into n into h. ठीक है, call this as equation number 2. We have r equals to epsilon 0 n square h square upon pi m e square. V equals to e square upon 2 epsilon 0 n into h. हे इक्वेशन कसं झालं तर फक्त इथे एम व्ही आर होता, तो आर आपण सेपरेट केला. ठीक आहे, आणि तिथे व्हीची व्हॅल्यू सबस्टिट्यूट केली की आपल्याला जे मिळतं ते इथे आपण आरच्या फॉर्ममध्ये एक्सप्रेस केलंय. दॅट्स इट. So just substitute both the equations in this fundamental equation, that is well-known equation. So T equals to 2 pi r upon V, and that is simply provide you the orbital period of an electron in hydrogen atom. So T equals to 2 pi r into epsilon 0 n square h square upon pi uh, upon pi m e square. 2 pi r ची व्हॅल्यू सबस्टिट्यूट केली, epsilon 0 n स्क्वेअर h स्क्वेअर अपॉन पाय m e स्क्वेअर, आणि आता राहिली कुठली व्हॅल्यू तर v ची व्हॅल्यू आपण सबस्टिट्यूट करायची. v काय आहे e स्क्वेअर अपॉन 2 epsilon 0 n into h. चेक करा, r ची व्हॅल्यू epsilon 0 n स्क्वेअर h स्क्वेअर अपॉन पाय m e स्क्वेअर. v इक्वल्स टू e स्क्वेअर अपॉन 2 epsilon 0 n into h. ठीक आहे, मग आता कॅन्सल करता होत बघा, हा पायला हा पाय कॅन्सल, 2 ला 2 कॅन्सल, epsilon 0 epsilon 0. Okay, so what is left here? That is simply 2 pi r upon v. H. No, there is one mistake. Just check here. आपण इंटू फी केला, तर आपल्याला अपॉन फी करायचंय. ठीक आहे, इंटू इंटू 1 अपॉन v. ठीक आहे, 2 पाय epsilon 0 n स्क्वेअर h स्क्वेअर अपॉन पाय m e स्क्वेअर. ही व्हॅल्यू आपण या इक्वेशनमध्ये न्यूमरेटरमध्ये टाकली. आता डिनॉमिनेटरमध्ये व्हेलॉसिटीची व्हॅल्यू टाकायची. ठीक आहे, सो 2 पाय epsilon 0 n स्क्वेअर h स्क्वेअर अपॉन पाय m e स्क्वेअर ॲज इज, आणि हा फी अपॉन फी आहे बरोबर, म्हणजे इथे 1 अपॉन e स्क्वेअर upon 2 epsilon 0 n into h. The same can be written as 2 pi epsilon 0 n square h square upon pi m e square into 2 epsilon 0 n h upon e square. ठीक है, okay, 2 into 2, that we'll write here. That's a final answer. 2 2s are 4, 4 pi cancels, epsilon 0 cancel होणारे पॅरामीटर कॅन्सल करूया. ठीक आहे, epsilon 0 that is epsilon 0 square, epsilon 0 square, n स्क्वेअरचं n क्यूब होणार, n क्यूब कारण इथे n आहे इथे n स्क्वेअर आहे, hचं पण इथे h क्यूब होणार अपॉन काय शिल्लक राहिलं m इंटू ई रेस टू 4, m इंटू ई रेस टू. ठीक आहे. आता आपण चेक करूया की बाबा आपण रिक्वायर्ड फॉर्ममध्ये आलो का. बघा, युझिंग बोहर्स मॉडेल the orbital period of electron in hydrogen atom in nth orbit म्हणून इथे n आला, इथे ऑर्बिटचा नंबर दिला असता तो रिप्लेस झाला असता. ठीक आहे. सो विल चेक this option is not, this is not, this one is also not. Yes, this is the correct one. ठीक है. So you can also here B is the correct answer. 4 epsilon 0 square n cube h cube upon m e raised to 4. This is very fundamental, that time period equals to 2 pi upon v. मग या ठिकाणी बोहर्स क्वांटायझेशन कंडिशनमध्ये आपल्याला आरची व्हॅल्यू ही मिळते, हे लक्षात घ्यायचं आहे. ठीक आहे. आणि व्हीची व्हॅल्यू पण ही आपण एक्सप्रेस केली by taking the help of this fundamental equation. And v square upon r equals to e square upon 4 pi epsilon 0 into r square. ठीक है. Next. So this is the correct answer. Next one. Any doubt? Hello. Hello. Any doubt? Okay. Next point. Next question. Sixth one. Bohr's model is applied to a particle of mass m at a charge q is moving in a plane under the influence of transverse magnetic field B. ठीक है. The energy of the charged particle in the nth level. आपल्याला इथे एनर्जी काढायची. Bohr's model is applied to a particle of mass m due to charge q is moving in a plane under the influence of transverse magnetic field. Okay. We know that mv square, the centripetal force mv square upon r is completely balanced by magnetic force असं म्हणतात ते. म्हणजे बी इतकं मॅग्नेटिक फील्ड अप्लाय केल्यानंतर सेंट्रिपिटल फोर्स हा बॅलन्स झाला असं म्हणतात. बोर्स मॉडेल इज अप्लाइड टू अ पार्टिकल ऑफ मास m and charge q is moving in a plane under the influence of transverse magnetic field. Whatever the centripetal force is necessary to perform the uniform circular motion is to be provided here by the maximum force, magnetic force, EVP. ठीक है. So that can be written as mv square equals to E B then V into R. Now, this is known that centripetal force must be balanced by magnetic force. Now, as per Bohr's model, we have mvr is equal to nh upon 2 pi. Therefore, vr equals to nh upon 2 pi n. Okay, Vr, that is called m phi square. Vr, velocity into radius. So Vr equals to nh upon 2 pi. Therefore, we can write m v square equals to E B n h upon 2 pi n. 2 pi n. Check करा. We have m phi square equals to EBE V into R by this equation. How this equation we have obtained? By simply considering the fact that whatever the centripetal force is necessary to perform the uniform circular motion by the electron is going to be balanced by the magnetic force. EVB, that is the maximum force exerted by the magnetic field on the moving particle, moving electron. And therefore, we can write mv square equals to EVB into R. But as per the Bohr's quantization condition, mvr is equal to nh upon 2 pi. Therefore, we obtain V into R is equal to NH upon 2 pi, and that M we have taken to this side. Okay? So M phi square, we are substituting this second equation in equation first. VR equals to NH upon 2 pi M. Okay, nh upon 2 by m. Substituting 2 in 1. So what we obtain? M phi square is equal to E B, and for V into R, we are substituting NH upon 2 pi m. Okay, so let us check whether this is m phi square, but they are asking to calculate energy of charge particle. Energy of the electron in which is moving in nth orbit can be written as E equals to half mv square. आता बघा ह्याला इक्वेशन बनवलं. हे सगळी सगळी इक्वेशन्स जर तुमच्या डोळ्यापुढे असतील तर तुम्ही पटपट सॉल्व्ह करू शकता. अदरवाईज फॉर्म्युलीज रिकॉल करण्यामध्ये जास्त वेळ जातो. ठीक आहे. सो दिस इज थर्ड वन. Again, we have E equals to half mv square. We will call this as equation 4. But from equation 3, what we have, that is mv square is equal to EP nh upon 2 pi m. That we will substitute here. So half into mv square is to be replaced by E P N H upon 2 pi m. Now it's correct. Okay? So energy of the electron which is orbiting in nth orbit can be written as E B N H upon 4 pi m. Now let us check for the answer. Okay. Notation is different here. Now, instead of E, they have used here. Instead of E, they have used here Q. So E must be replaced by Q. So this is Q, charge on electron, B N H upon 4 pi m. Okay? Q B N H upon 4 pi m. Let us see whether that answer is there or not. NHQB upon 4 pi m. So this is the correct answer. NHQB upon 4 pi m. Okay. So This is the correct answer. Again, remember, we have centripetal force necessary to perform the circular motion, balanced by magnetic force, Lorentz force, which is given by E into V cross V, but P and P are perpendicular to each other, and hence they exert maximum force on moving electron. So it can be given by EVB. Okay? So as per that, we obtained first equation, mv square is equal to EBV into R. But again, as per Bohr's quantization condition, mvr is equal to nh upon 2 pi. So we have calculated Vr was to nh upon 2 pi m. Therefore, substituting 2 in 1 can provide mv square is equal to EPNH upon 2 pi m. Substituting this mv square in energy value, E equals to half mv square. So we have reached to this particular question. And that is correct one. Next, now this is again easy one. See, okay, check the conditions. The wavelength of first line in Balmer series in the hydrogen spectrum is lambda. Now, you should recall that for Balmer series, for Balmer series, for Balmer series, N1 equals to 2. First line will be observed by substituting N2 equals to 3, N1 equals to 2, N2 equals to 3, and wavelength obtained is lambda. Okay. What is the wavelength of the second line in the same series? This is first line. Now second, you will replace here first line by lambda 1. Second line can be obtained by having the same series n1 equals to 2, but n2 equals to 4. It provides second line wavelength of second spectral line, lambda 2. Okay, so we require to calculate ratios of lambda point to lambda 2. Very easy job. For Balmer series, we have the equation, very fundamental equation in terms of Rydberg's constant, of which the value is given as 1.097. R into bracket 1 upon n1 square minus 1 upon n2 square. So right equation, our 1 upon lambda has to be replaced by lambda 1. Lambda 1 equals to R into bracket 1 upon n1 is to be replaced by 2, 2 square minus 1 upon n2 is to be replaced by 3 square, 3. Okay? n1 equals to 2, n2 equals to 3 to get lambda value. Similarly, lambda 2 can be calculated by just having 1 upon lambda 2 equals to R into bracket 1 upon. Substitution is same for same series, 1 upon 2 square minus 1 upon 4 square. Okay? So, by solving this, you can write 1 upon lambda 1 equals to R into bracket 1 upon 4 minus 1 upon 9 equals to R into bracket 9 minus 4 upon 36. Okay? So R 9 minus 4, 5 upon 36. this first one. Similarly, we can calculate lambda 2 equals to r into bracket 16 minus 4 upon 4 into 16 equals to r into 16 minus 4, 12 upon 4 into 16. Okay? All this is equation 2. Taking the ratio, so you can obtain here lambda 2, lambda 1 upon lambda 2. Lambda 1 upon lambda 2 equals to r into 12 upon 4 into 16 upon r into 5 upon 36. Okay. So solving this, what is the 3 upon 16? 4 3s are 12. 4 3s are 12. R into 3 upon 16 upon R into 5 upon 36 equals to R cancel होता है थे, no need to consider it. 3 upon 16 into 36 upon 5. Okay. So this is solved and the answer we will be getting, that is simply 25, 27, 36 into 3, 36 into 3. 36 into 3, 108 upon 108 divided by 18, and that gives rise to 20 by 27. So ratio of you calculated the ratio, but they are asking simply to calculate the wavelength of second line. So no need to do all these things. Okay. फक्त इथे लॅम्बडा 1च्या ऐवजी आपण लॅम्बडा सबस्टिट्यूट करायचे आणि चेक करतो. So okay, so method is same, nothing new I have told you. Just what you have to do, you have to use the equation 1 upon lambda equals to r into bracket 1 upon 2 square minus 1 upon 3 square for lambda pattern, and second 1 upon lambda 1 equals to r into bracket 1 upon 2 square minus 1 upon 4 square. Okay, so the solution of this question is, you please check it. The answer we found is, method is same. Okay. So answer given is 20 by 27. You please check that. ठीक है, किती वेळ आहे सर?
झाले
ओव्हर.
और संपर्क
ओके,
और
ठीक आहे. तुम्ही सातवं एक्झाम्पल करून बघा. नाही आलं तर मी सॉल्व करून पाठवते. बट मेथड इज सेम. ओके. Otherwise, we will discuss it, the same example in the next lecture. Till that, thank you very much.